All right, let's dive in. Today, we're opening up the programmer's toolbox and taking a close look at one of the most fundamental concepts in all of coding, data types.
So let's kick things off with a puzzle that trips up pretty much every new programmer. You've got a variable x, and it equals the number 5. Then you have another variable y, and it equals the character 5. Now, to you and me, they look almost identical. But for a computer, they are worlds apart. The question is, why? Well, the answer to that little puzzle is all about the secret language we use to talk to computers. And that language starts with data types. This is how we give our data context. It's how we tell the machine not just what the value is, but what kind of value it is. And this is the absolute key. Before a computer can do anything with a piece of information, it has to know what it's dealing with. Is it a whole number, a number with a decimal point, a single letter? This single instruction, the data type, tells the computer exactly how much memory to set aside and what kind of operations it's even allowed to do. Okay, so right at the very foundation, at the bottom of our toolbox, we have the primitive data types. You can think of these as the raw materials for programming. They're the atoms of our code, simple, essential, and the building blocks for literally everything else. So let's crack open that toolbox and check out our first set of tools. Think of these as the hammers, the screwdrivers, the wrenches of your code. You're going to find yourself reaching for these in almost every single program you ever write. And I'm not kidding. Every complex program you can imagine, from a simple calculator app to a massive online game, is built right on top of these simple yet incredibly powerful primitives. Getting a handle on them is really the first big step to becoming a great developer. Now, this table here is really interesting because it's all about trade-offs. A byte is tiny, super memory efficient, but it can only hold small numbers. An int gives you a way bigger range, but it uses 4 times the memory. So why does that matter? Well, imagine a game with millions of players. If you store each player's level as a byte instead of an int, you could save gigabytes of memory on your servers. It's all about picking the right tool for the job. And, sometimes programmers even create their own simple types, which we call user-defined ordinal types, maybe for something like the days of the week, just to make the code extra clear. So what happens when we take that primitive chart type, which remember holds just one single letter, and we string a bunch of them together? Well, you get a character string. This is how we build words, sentences, all the text you see on your screen. It's our first real look at building something bigger and more complex from the basic parts. Okay, once you've got your basic tools down, you need a way to organize them. I mean, you can't build a house with just a messy pile of bricks, right? You need a blueprint. And in programming, composite types are that blueprint. They let us create more complex structures to solve bigger problems. Now, 2 of the most common organizers you're going to use are arrays and records. An array is perfect when you have a long list of similar items, like, say, the marks of all the students in your class. They're all numbers, all the same type. A record, or a struct, as you'll often hear it called, is for when you need to group different types of data together. Think about a student's profile. You've got their name, which is text, their roll number, which is a number, and their grade, maybe a character. And hey, for those times you need a quick temporary grouping, there's also something called a tuple. Think of it as a lightweight, unnamed record you can just throw together on the fly. This brings us to a really clever but kind of tricky tool. What if you have a container, but you know you're only ever going to put one thing in it at a time? Maybe today it holds a number, but tomorrow it's going to hold a character. You don't want to waste a bunch of memory allocating space for everything at once. And this slide illustrates the difference perfectly. The struct on the left, that's our lunchbox. It carves out separate, dedicated memory space for an integer, a float, and a character. All 3 of them can exist in there at the same time, no problem. The union on the right, though, is a master of efficiency. It looks at all its possible members, the int, the float, the char, and it only allocates enough memory for the biggest one. In this case, that's the float. So that one chunk of memory can hold an integer, or a float, or a character, but never more than one at a time. It's one container, but with multiple possible identities. And for even more flexibility, we've got things like lists, which are basically arrays that can grow and shrink whenever you need them to. And we have associative arrays. You'll hear them called maps or dictionaries. Instead of using a number index, they let you store and look up data using a unique key, just like looking up a word in a dictionary to find its meaning. All right, now we're getting to the heavy machinery of the toolbox. Things like pointers. These are incredibly powerful. They give you amazing performance and control, but you absolutely have to know the safety rules before you use them. So, what exactly is a pointer? Well, instead of holding a value itself, like the number 5, a pointer holds the memory address where the number 5 is stored. It's like having the address to a house instead of the house itself. This gives you an incredible amount of power and efficiency, letting you work directly with the computer's memory. But, and this is a huge but, with that great power comes great responsibility. If you mishandle a pointer, if you point it to the wrong place in memory, you can cause some of the absolute worst, most difficult to find bugs and crashes in all of programming. And that is why we have workshop safety rules, to stop us from using our tools incorrectly, like, say, trying to do math on a word. In programming, we call these safety rules type checking. It's the language's way of making sure you don't try to hammer in a screw. This is basically the language double-checking your work, often before you even run the program. A big part of this is deciding when two types are considered the same, which is called type equivalence. Some languages are really strict. If two types don't have the exact same name, they're different. That's name equivalence. Others are more flexible. If two types have the same internal structure, they're considered the same. That's structure equivalence. It's a really fundamental design choice. This all leads us to the idea of strong typing. And you can think of this like a super strict workshop supervisor. It enforces all the rules, making sure you can't possibly use a hammer where a screwdriver is needed. Languages like Java are strongly typed, and this makes programs way more reliable by catching these kinds of mistakes early. So we have this whole toolbox, from simple screwdrivers to complex power tools, and we have a whole set of safety rules to guide us. But knowing how to use a hammer doesn't make you a master carpenter, right? Becoming a true craftsman is about something more. And that's really the heart of it. Being a great programmer isn't about memorizing a list of every data type. It's about developing an intuition for the trade-offs, choosing the right type for efficiency, for readability, and for reliability. It's about making smart decisions to build code that's not just functional, but elegant and robust. And that brings us to a final thought. The whole history of programming languages is just a long story of trade-offs. C++ gave us the raw power of pointers, but it wasn't always safe. So Java came along and gave us more safety through strong typing, but it traded away some of that raw control and performance. This evolution is always a search for that perfect balance between power, safety, and simplicity. So the question I'll leave you with is this: what do you think is the next big trade-off for the programming languages of tomorrow?